All right, welcome to next-gen manufacturing. When we think about making things, we often picture sparks flying, right? But today's manufacturing, it's a whole different ballgame. We're talking about a level of precision that's almost impossible to wrap your head around, and it's all happening at incredible speeds. So what's the secret sauce here? How do these incredible machines carve out everything from the phone in your pocket to a critical part of a jet engine, and do it so perfectly? Well, that's exactly what we're going to unpack. And let me tell you, the answer, it's a lot smaller than you'd probably guess. All right, so let's set the scene. In modern CNC machining, the pressure is always on. I'm talking about cutting super tough materials, creating these insanely complex shapes, and doing it all at blistering speeds. But here's the catch. The faster you go, the more critical accuracy becomes. Just one tiny vibration, one slip that's smaller than a hair, and poof, a part that costs thousands of dollars is completely worthless.
So you'd think the solution to handling all that speed and force would be in the massive machine itself, right? The big, powerful parts. But it's not. The real key, the thing that unlocks this whole next-gen level of manufacturing, it actually comes down to one single, supercritical connection.
And this is it. We're talking about the exact point where the cutting tool, the bit that does the actual cutting, meets the tool holder that clamps it into the machine. It's such a small spot, but believe me, this is where the magic happens, or where it all falls apart. Here's a way to think about it. Imagine you've got a supercar with 1,000 horsepower, but what if it has cheap, bald tires? All that power is totally useless, right? You can't put it down on the road. It's the exact same principle here. A sloppy connection is a massive bottleneck. It kills your speed, it ruins your accuracy, but a perfect, rock-solid fit, oh, that changes everything. That's when you unleash the machine's true power.
Okay, so how on earth do engineers make sure they get that perfect fit? Not just sometimes, but every single time, on thousands of parts. Well, they have a secret language, a language built entirely on precision. And the key word in that language is tolerance. So what is tolerance? Let's break it down. It's basically the acceptable range of variation for a part's size. Think of it as the official rulebook. It's not a nice-to-have or a suggestion, it's an ironclad guarantee. It's how an engineer says, I don't care where in the world you make this part, if you follow this tolerance, it will fit. It takes all the guesswork out of the equation. Now, there are two main ways to think about tolerance, but for our story, we're zeroing in on the one on the right, the Schenck basis system. You'll see it marked with a lowercase h, and here's the absolute key takeaway. This system works with a negative tolerance. What does that mean? It means the shank, the part of the tool that gets held, can never be bigger than its official size. It can be dead on or a tiny, tiny bit smaller, but never bigger. That one little rule is a complete game changer. Which brings us to the hero of our story, really, the H6 standard. This is the absolute gold standard for high-performance work. When you see H6 on a tool, you know it's not messing around. It's built for the toughest, most precise jobs out there. So, let's decode what H6 actually tells us.
First up, that H. We just talked about this, right? That little letter is our promise. It tells us we're on the Schenck basis system, which means the shank of that tool is guaranteed to never, ever be oversized. It will always fit into a hole of the same nominal size. It seems so simple, but that one letter carries a huge amount of weight.
Okay, so what about the 6? That number is the International Tolerance Grade, or IT grade, and basically it tells you how tight the tolerance is. The rule here is super simple. The smaller the number, the more precise the part has to be. So an IT grade of 6 is way more precise than, say, an IT grade of 11. For jobs that demand insane accuracy, like reaming a perfect hole, you're always going to see these really small IT numbers.
So, let's put this into perspective. What does H6 actually mean in the real world? Well, for a tool shank that's 1 inch in diameter, the H6 tolerance allows it to be 0.0005 inches smaller than 1 inch, 5/10,000ths of an inch. To give you an idea of how small that is, that's about 1/6 the thickness of a single human hair. We are operating in a world of unbelievably tiny measurements, and that's exactly what it takes. Okay, so we've got this amazingly precise tool shank. Perfect. But now you need an equally precise way to hold it, right? And this is where the engineering gets, well, it's just beautiful. We're going to use some high school physics, literally just thermal expansion, to create the strongest, most perfect grip imaginable. Say hello to the shrink fit holder.
And the process itself is so elegant, it's brilliant. It's just 4 simple steps. Step 1, you heat the tool holder with an induction heater. Step 2, the heat makes the hole in the holder expand just a tiny, tiny bit. Step 3, you take that H6 tool shank, which was too big to fit when it was cold, and it just slides right in. And then, the final step, you let the holder cool down, and as it does, it shrinks.
And as it cools, the tool is held tighter and tighter in place. It clamps down with an incredible amount of force. We're not talking about a couple of set screws here. This thing is being gripped with immense uniform pressure all the way around the shank. It's basically like the tool and the holder have become one solid piece of steel.
So we've just been deep in the weeds, right? Talking about microns and thermal physics. But let's zoom back out. What's the big payoff? Why go to all this trouble? What do you actually get from all this microscopic precision?
Well, you get 3 huge advantages. First, you get insane gripping power. That tool isn't going anywhere. Second, you get incredibly low runout. Now, runout is just a fancy word for wobble at the tip of the tool. By getting rid of that wobble, you get way better surface finishes and your tools last a heck of a lot longer. And third, you get superior balance. Because everything is so perfectly centered and secure, the whole assembly is balanced, which means you can spin it faster and cut more aggressively. You can really push the machine to its limits.
And that's the whole point. The secret to making things faster, better, and more precise isn't some single magical breakthrough. It's the combination of all these little things. It's the obsession over a few microns on a tool shank, combined with a brilliantly simple use of physics. That is how next-gen manufacturing happens.
So kind of makes you think, doesn't it? If there is this much mind-blowing engineering packed into one tiny connection that most of us never even see, just imagine what other hidden innovations are all around us, quietly making our world work. Something to think about. Thanks for joining me.